I like origami a lot. In particular, I like modular origami, which ultimately consists of folding lots of squares of paper into the same thing lots and lots of times, and then connecting those pieces of paper to create complex structures. One of my favorite models is the Bashetta star. The units are super easy to fold, the finished model is very sturdy, and the same unit can make polyhedra of many different sizes. I like to make my Bashetta stars using 3 different colors of paper, equally distributing the colors throughout the model. But sometimes, like with this model, I assemble the model only to get stuck putting 2 units of the same color next to each other. So I decided to create an algorithm that would give me an assembly roadmap of sorts to resolve this issue. Turns out, similar to all graph coloring problems, this is a hard problem. Like NP hard. So let's write an algorithm that can hopefully get us close to a correct answer. It sounds pretty similar to a graph coloring problem, but our graph is really a 3-dimensional model. So first we need to make a graph that represents the origami. Let's take the 30-piece Bashetta star as our example. If we ignore the spiky bits, the origami model resembles an icosahedron. And we can represent an icosahedron as a planar graph. A planar graph is a graph where the edges only cross at the nodes. The faces of the polyhedron are the regions enclosed by the edges and nodes. This is good, but now we need to add the spikes from our Bashetta star onto this graph. We can spike the planar graph by subdividing the faces on the graph into triangles. Notice that the area around the graph also counts as a face of the polyhedron, so I'll subdivide that too. Great. Now our graph represents the edges and vertices of our actual origami model. But with this current graph, I would be traversing through the vertices of the origami model, not the faces. We can take the dual of the graph to solve this, which is where any nodes in the graph become faces, and vice versa. The final step is a direct consequence of the Bashetta star unit. One unit corresponds to 2 faces, which means we'll replace edges connecting 2 nodes between triangles with a single node. And after all that work, we have a graph that matches our origami model. Now time for the code. We'll implement a greedy heuristic and a local search algorithm for this problem. Let's start with the greedy algorithm. We'll perform a breadth-first search to traverse through all the nodes, picking the color that has been used the least thus far. If we get stuck, we'll just default to the first color and keep track of that location. For the local search algorithm, we'll start at a node that got flagged in the greedy algorithm and replace its color with whichever of the other 2 colors will raise the least number of new errors. Then we'll go to the nodes that raise new errors and resolve those using the same method, continuing that until we find a solution. If we're lucky, we'll get a result that has equal distribution of color without any violations of the coloring rules. At one point, my program gave a valid solution, so I just had to test it. First, I colored the graph to see if the rules were followed correctly. Then, I assembled a Bashetta star to solidify that correctness. This algorithm implementation wasn't perfect, but when I got lucky, the algorithm gave me a perfect roadmap to assembling my origami.